Okay, so let's see. I guess we are good to go. Okay, so today we'll talk about VHDL, which stands for HDL stands for Hardware Description Language. And let me. So I prepared the slides, but when I uploaded it, didn't really populate well. So I had to re-download it from Canvas. So that's why it's a PDF today, but it's fine. It's essentially uh, the same thing, but it's a different interface. That's why. So what is a hardware description language? As the name suggests, you basically describe the hardware using a language. Basically, that's exactly what the name suggests, and that's exactly what it is. And there are different kinds of hardware description languages for different types of hardware design. For the sake of digital design, we use mostly two kinds, VHDL and Verilog. Okay, but for this course, we'll only talk about VHDL. If you take, say, 651, there I teach Verilog and VHDL both to some degree, but it's fine. If you learn one, it's easier for you to catch up with the others. It's kind of like learning C, C++, C#, Java. How many can you learn? If you learn one very well, you can easily switch over to other. And obviously, within your career, things will change. There will be new languages popping up every once in a while. So it's not a big deal. Now, it's kind of analogous to writing software programs in a high-level language like C, for example. Essentially, if you have any experience with any kind of programming languages, it will be much easier for you to handle. Now, these are notes for you to read at home. I'm not going to read through them, obviously, but I'm going to give you a high-level overview. And, disclaimer, today's lecture is going to be heavily dependent on talking, basically, like less illustration, more talking points. So, just plan accordingly. That's why there are so many written sentences here and there, which is not typical. So, VHDL stands for VHSIC hardware description language, and VHSIC itself is acronym for Very High Speed Integrated Circuit. So it's a mouthful, right? All right, so it's basic. It dates back decades, essentially. It became an IEEE standard back in 1987, which is decades ago, as you see, but it was further revised in 1993, in case you are interested to know about some history. And it was originally funded by the US Department of Defense. So that shows you many of the stuff that we use today, they were research projects at some point, right? Everything was research at some point, and now they're mainstream. Everybody uses them. And now it has become a general purpose hardware description language that everybody uses. And it's an industry standard. If you work for Intel, NVIDIA, like any big companies, you'll need to use this same language. Okay, so please read these notes. Don't skip them at home. I'm skipping because I'm gonna talk about it anyways, right? Verbally. So I don't have to read through this paragraphs, but please make sure to read them well for your own sake. So VHDL has different levels of description. Say, for example, behavioral, data flow, and structural. And we'll see some examples. So for example, you can write a code that just describes the behavior of the hardware instead of getting to the granularity of how AND gates, OR gates, XOR gates are connected with each other. But if you want to, you can describe it to that level of granularity where, oh, this AND gate will drive that OR gate, will drive that XOR gate, and so on. So it's your choice. And obviously, the more complicated the system becomes, getting to the lower level of granularity becomes more challenging. And I know it's a lot of talking points. You don't see anything here yet, but there are examples that are coming up. I want to cover these points first so that you have it in your mind when we go through the examples, right? Okay, so keep that in mind. There are different levels that you can use. If you're comfortable coding at the very high level that just describes the behavior of the circuit, as the name suggests, it's a behavioral coding. You don't see deeper down how the AND gates and OR gates and XOR gates are connected. But if you want, you can also go down to that level. That's the interesting part about VHDL, and that's the power of VHDL, basically. So start seeing some snippets as we move forward through this slide. We'll start small with very simple structures and then get to a complete module that shows you the overall structure of the code. All right. And then we'll end with an IEEE standard coding that you'll probably always use going forward. Okay, so imagine you are trying to write a code for a logic system like this, where one gate driving the other. This is how you can describe the hardware, essentially, as simple as that, 2 sentences. Of course, there are other fitting stuff you have to include and initiate, but at the very least, this is how you can describe it. And sorry, let me, yeah, I can zoom in here as well. Getting used to this interface as well. Where's this? This is, sorry, give me a second. I'm trying to get back to, oh yeah, there it is. Okay, so notice you are trying to describe the output C. Okay, what is that? This is an AND gate. Basically, as the name suggests, you describe the hardware. So you do A and B. Forget about the rest of it. A and B. And is a keyword. You can imagine OR is another keyword. XOR is another keyword. These are reserved keywords. And by the way, anything that you see in bold, they are reserved keywords for very long. For VHDL. Okay, so just keep that in mind. And I'll show you a list of things in a table towards the end of the lecture, so that you don't have to memorize anything. And of course, your textbooks is also always there. We can never cover every available features of any language in a lecture or two, for example, right? You have to learn by doing it. Anytime you want to use something like this, oh, how do you do it? You just go to the user manual and figure it out, because it's a process. But I'm going to give you an introduction, as the lecture suggests, and hopefully help you look for the things that you might need to learn in the future. So how about describing the next output, E? This is essentially an OR gate. So you are taking an OR between these two inputs, C and D. You see, basically, it's as simple as describing what is going on, what you're looking at. But you just have to abide by some syntax, as you can imagine. In any programming language, we have some agreed upon syntax that we follow, and VHDL is no exception. Are you okay so far? All right. Now, what's the rest of the code doing here? So for the rest of it, notice we have a section that talks about, say, after 5 nanosecond. That 5 nanosecond represents the practical delay of a logic gate. By now, we all know that when you provide 2 inputs in a logic gate, you don't get the output right away, right? Did we cover this in a separate lecture? Didn't we? So there is a delay associated with it. So this code can be realistic and allow you to implement those delays as well. So here we are describing that, hey, it takes 5 nanosecond for C to be available and 5 nanosecond more for E to be available. Okay. Any surprises here, folks? Okay. Excuse me. So there is another way to describe this. So it's getting to a certain degree of granularity where you are describing individual gates, right? As you see in this example, you're describing the individual gates. But what if you want to, you could also do it this way. This is called a behavioral description. It basically, merges both in just one sentence. That's all. And you can use parentheses to help the simulator decide which operation to do first. There is also some agreed upon precedent, which I'll show you in the end. There are like 7 types, but it's always a good idea to use parentheses so that you know which one will be taken care of first. So first you do this within the parentheses, A and B. So you get something out. And then whatever you get as an output, you do an OR with D. So you don't have to describe C as an intermediate variable. Okay? Am I making any sense here, folks? Or okay. Do you see how many? Okay, can you tell me that have every one of you taken C, C++, or any other language? Okay. So is it surprising to you at all? Isn't that kind of yes, it's a different syntax, and its purpose is very different. Its purpose is to describe the hardware. But essentially, in terms of coding norms, if you ask me, why do you do it this way? Because people came together and agreed on that standard. That's why it became the IEEE standard. This is how we all code around the world in any industry, so that we could talk to each other, basically. This is an agreed upon standard. There are no logic behind it. You might feel like, oh, this is an inefficient way to do it. Okay, good luck. People decided to do it this way. So we have to live with it. Okay, so let's move to the next example, right? Uh, so we already covered this example, and this basically describes what happens when this is executed. So since I told you that there is a 5 nanosecond delay to get to C, and then 5 nanosecond delay to calculate E, if you see the output of this code, you'll see E having a 10 nanosecond overall delay, because 5 nanosecond to get to C, and then 5 nanosecond more to get to E. So overall 10 nanosecond. Obviously, I don't have to tell you this now because you already have this idea from the hardware description. Okay. Now let's move to the next example. There is another way to describe this. You could always define a port map. So imagine this is an AND gate. You can define it as a gate, logic gate. N2 represents 2 input AND gate, for example. And you define the ports of this gate. And the ports are A, B, and C. And you can always mention which ones are inputs and which ones are output. And don't worry, I'm starting small, and then we'll see a full-fledged code which will show you everything together, right? It will make sense. And for the next one, you need an OR gate, which is again 2 input, so OR2. And the port map shows you have C, D, and E. This is another way to code it, okay? If in case you ever need to. It's the reason I'm showing you, or the textbook shows you different types or different styles of code. It's not because you need to use all of them. You can choose one and stick to that. You can pick your own style, but you should be able to understand somebody else's code when they share it with you. That's the point. Maybe you choose to use, and or type description, but your friend or your colleague from a different, group chooses a behavioral description, for example. So you should be able to talk to each other. That's all. Okay, that's why we need to be aware of different styles of coding. Okay, let's move to the next one. And every slide, please read them. I chose this description carefully so that, by reading through all of them, you'll have a holistic understanding of what needs to be, kept in mind. Here, the most important take-home message is the fact that the arguments, the sentences that we are writing here, they are concurrent, meaning they are handled simultaneously. Unlike in some programming languages, wherever, say, you define a variable, have you used MATLAB? I'm sure, right? So if you define a variable A and then use it later, say, for example, you define A equals 10 and then do B equals A plus 2, it's fine. But if you don't do it in sequence, if you don't define A, but try to use it somewhere and later define A somewhere else, you see my point? You might get an error message in some programming languages. So what I'm saying is some programming languages care about the sequence. So you have to make sure you define them in a way that they are executed in sequence. But some programming languages basically deal with everything concurrently. So this is an example of where things are treated concurrently. So both of these sentences are concurrently handled. So you don't have to worry about the sequence. So what you see here between these two lines is that it's basically flipped. Give me a second. It's basically flipped. You see that? It doesn't matter. Although you feel like, hey, E needs to know the value of C to operate. So here we are defining E with C, but C hasn't even been defined yet. It has been defined in the next sentence. But like I said, it's concurrent. They are all handled simultaneously. So you don't have any problem with that. Any question so far, folks? Okay, so concurrent. That's another point to keep in mind. Okay, there is another important feature that we often use in VHDL, that is defining signals. And this is the standard norm of defining signals, and you'll see some specific examples. But before you go to the example, this is how you define it. You give it a name, give it a signal name, and you define how that signal should behave. Is it an AND between two inputs? Is it an OR between two inputs? Is it a more complicated function? You basically define the function here. And then you define the delay. Say after 5 nanosecond, 10 nanosecond, 50 nanosecond, you define that. And anything that you see in, excuse me, square brackets, this is optional. Okay, it's there, it's mentioned somewhere in the text, read it. If you don't define the delay, VHDL will automatically impose a very small delay, which is like delta. And that depends, how much that It depends on the system, but it's very small delay to make sure you don't have any convergence issues. So it automatically imposes some specific delay. But it's always a good idea if you know the delay specifically to provide the delay number. Okay, so for realistic design, imagine, okay, let's take a step back and let me try to connect it to real life. Did I tell you that in a certain industry like Intel, for example, they have dedicated engineers whose responsibility is to deal with different types of circuits. So for example, I might be responsible to design the best mux or best multiplexer. Okay, so my responsibility is to make sure Intel's multiplexers work appropriately and they're fully optimized. And I'm also responsible for characterizing. And what do I mean by characterizing? When we design these circuits, we simulate them and we also implement them in hardware. We test them, we measure their delay, we measure their performance, we measure, there are different set of parameters that we have to report. And imagine when I report the delay, if you provide an input to this multiplexer, you get the output after 10 nanoseconds. So I already get these numbers from characterization. Do you see what I'm trying to say here? So once I know this, I can always include it in the code. And I am responsible for making the Verilog component for the multiplexer. And towards the end of this lecture, you will see there is a library. You don't have to like do it from scratch every time. You're learning it, but you don't have to probably do it ever. You can always use things from the library. There are standard cells that you can just call. And those standard cells have been characterized this way. They already have the delay in it. They have other parameters in them that were characterized by the engineers who were responsible for that thing. Does that make sense? Okay, so Intel, NVIDIA, AMD, they all maintain their own, standard characterization numbers. But if you don't mention anything, it will just take some random values. Okay, so let's take another example. We will see, like I said, some easy examples, and then we'll see something relatable to our course. So imagine you just take an inverter, CMOS inverter. Inverter is mentioned as a NOT gate in VHDL, okay? So you are creating a clock. How can you create a clock? This is a simple example of how to create a clock signal. And the reason I show it here is we will be using clock signals quite a lot in some circuits, okay? We'll talk about sequential circuits pretty soon, coming up, flip-flops, latches, and they are driven by clock. So basically, when the clock is high, something happens. When the clock is low, you just stop and wait, something like that, right? You take turns to work, essentially. So clock signal is a very important part of chip design. You basically have dedicated clock generators on chip. Just to show you how to easily incorporate a clock in VHDL, it's as simple as, defining a signal clock. And let me, oh, yeah. I'm just mixing it up with the PowerPoint every once in a while. So imagine you basically just assign the output as input to itself. Okay, so your clock is not clock, and then you define a delay which is not 10 nanosecond. So it takes an output. It can initialize as 0, and since you're doing not, it is going to invert that 0 to 1, which is like Boolean logic 1, by the way. It flips between 0 and 1. Remember that. The levels are Boolean, 0 and 1. Okay, so that's why you don't see any voltage levels here. It's just Boolean. Okay, there are actually 9 types of levels that we can achieve with IEEE standard, and this is in the last slide. We'll talk about it. But for the most part, you'll be using 0 and 1. Okay, so what the 10 nanosecond delay does is that it starts after 10 nanosecond, as you see here. Let me change the color. It starts after 10 nanosecond and then switches to 1, and then it just keeps doing it over and over again. So every 10 nanosecond, it provides the output to itself as an input. And that's why you have like 10 nanosecond delay every time. See my point? This is a clever, interesting trick. That's all. It's not a complicated circuit. And this is not the only way to create a clock, but this is just a fun experiment to create a clock using, self-assigned signals. And by the way, just to also show you, VHDL is not case sensitive. That's why you see, even if you write it in lowercase versus uppercase, doesn't matter. Just keep that in mind. Okay. Another interesting thing to keep in mind. Is MATLAB case sensitive? Do you guys know that? Yes. Okay. Anybody knows any other language that is not case sensitive? Anyone? Anyways, you don't have to tell me now, but there are some languages that don't care about, this case. In hardware design, there is another very big player in the market. It's called HSpice, Spice coding. Okay, this is also an industry standard platform that is also not case sensitive, and you haven't obviously used it, but just letting you know beforehand. Okay, so now we'll start looking at something that is more relatable. So far, we have looked at snippets here and there, but now you have all seen mux, right? So let's try to define a code, a VHDL code for a multiplexer. We'll start with the simplest possible multiplexer, 2 to 1. Okay. So have we seen this functional output before? How do you define a multiplexer? I hope you remember that. Say, imagine if you have A and B here and your select signal, and this is your output function. Your output will be, anybody remembers? A prime, sorry, S prime A plus S B. Remember that, folks? So when S is 0, you select A. When S is 1, you select B, right? And this is essentially exactly the same expression, except for the fact that your select is A here, select signal is A, and your input and outputs are I0 and I1, okay? So this is taken from the textbook. That's why it's different. That's why it looks the way it does, okay? But anyways, does that make sense? Have we seen this before, honestly? Okay. How do you incorporate that? Just define or describe the function. Notice you need A prime. So define not A. Not A is basically A prime. Okay. And then you need to do an AND between A prime and I0. So do AND between A prime and I0. And then, oh, by the way, you have to describe the precedent. Which one will be taken care of first? So we do the AND first. As you might remember, there was an AND array, and then there is OR, right? So you have to do OR later on. So that's why the parenthesis shows you do the AND first, and also you have to do another AND here between A and I1, and then you do the OR. Is that simple? Okay. Look at it at home again and just correlate with the hardware. It will make perfect sense. Okay, it's like super simple. There is another way to do it. And like I said, I'll keep showing you different alternatives of the same code. This is another way to do it. This is a conditional signal. Yeah, it's a conditional signal like this, as you see. So your functional output will be I0, which is this one. Can anybody just describe this verbally to me? When your function output will be I0? When? When? Tell me. This is the select signal. When A equals 0. Do you guys agree with it? You see, this is exactly what is being told to the hardware. F equals I0 when A equals 0. Right? That's why the name says hardware description language. You basically describe what you need. That's all. Okay, now imagine when this was not available to the engineers, right? They had to do everything manually from brute force, right? So somebody had to come up with this level of abstraction that makes it easy for us to design things now. See my point here? So it's so easy for us. We could just write something, and I'm sure you don't even have to write code anymore. Nowadays, it's so automated. You can ask ChatGPT, it will write a code for you. So I'm sure in 5 to not even 5 years, in a few years, people will kind of forget the syntax. As of now, even we don't remember all the syntax every time. I have to look it up. Like, okay, how do you define this? Oh, okay, this is how you do it. Nobody remembers everything. We always go back to a code that we wrote before and edit on top of it. Right? How many syntax can you remember? And they change all the time when you move from one language to the other, right? So nobody tries to memorize any of this. And in future, you don't even have to memorize anything, or even if you don't even have to check out the reference. You ask a large language model to write the code in a certain language, it will do it for you. So why bother? So we are getting to even higher degree of autonomy gradually. But this is already very automated. But notice when you describe this using this simple sentence, the simulator will have to convert it into AND gate, OR gate, and deeper down to bit level precision. But this is all being taken care of in the backend. So you must have taken, as you said, you've taken C. When you compile the code, before you run it, you have to compile it, don't you think? So after you compile the code, what happens? Do you know? I'm sure you have been told what happens when you compile. What do you compile? Why do you compile? Because yes, to check whether there is any error in the code. But basically, okay, if there is no error, then what happened in the or in the background? So, and how does the machine know that there is an error? Okay, first of all, when you compile, it basically converts the high level, what you look at when you describe for loop, when you describe these and that, if else condition. This is readable to human beings. It is not readable to the computer deeper down. The computer only has one language. What is that? Binary. Yes, it's called machine language basically. So it's streams of ones and zeros, nothing else. So the computer converts everything into streams of ones and zeros. Have you learned machine language coding by any chance? Any? Okay, no. I took a course when I was like in undergrad, and obviously it's not fun as you can imagine. You know, coding in machine language just to know this is how things work. And we were so appreciative of the engineers who helped create this abstraction that we don't have to deal with machine language ourselves. But just think of it for a second that at some point people used to deal with that themselves because there were no such high level languages. And languages are getting, what do I mean by high level? Obviously, meaning you don't have to deal with this level of detail. You just describe in your own language and it converts things. You must have seen it, just Google it. There are platforms that helps convert your written commands into conventional C code or other codes. You can describe, hey, write a for loop that will change a function from blah, blah, blah. Just describe it in sentences and it will convert it for you. And that's before ChatGPT, by the way. So people always thought about getting to even higher level so that it becomes accessible. In fact, 10 years ago, there was an interface for kids specifically, kids like primary school kids. That way they could play with these for loops and if else conditions. So they have this perception of logic. Okay. And how do you think that people used to teach these kids how syntax work? They don't. They basically use them as drag and drop blocks, like toys, like Legos. They learn, okay, do you want to keep increasing these numbers? Drag this block. Its purpose is to keep counting, something like that. So this is again a higher level language. What you're looking at here is any question? Yes.
So machine learning is a literally like for loop is a certain ASCII or electro.
It's a great question. So it's not really asking. What you are thinking is, does the machine convert every alphabet into ASCII code or something like that? No. So basically, there is a set of instruction. For example, for adding, there is a code. So if you give this code to the machine, it will use the adder block. So it will activate different blocks based on the code. So for example, you have 8 digits, 101111 blah, 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 blah. There is it's called opcode, right? Operational code. For that particular opcode, it will activate a portion of the hardware. Maybe that's an adder, and it will add. So that opcode basically represents the plus symbol. You see? So plus is not being converted into a ASCII code. It is being converted into an opcode, right? You see my point here? So there is a difference between when you code and it is converted into a machine language versus a conventional ASCII coding. Okay, so that's a very important question. I don't know it made sense to everybody, but if you didn't have that question, it's okay. But in case you had that question, anyways, give me a second. Sorry, I took a tangent. Where was it? Yes, I just wanted to appreciate the fact that it is so simple and meaningful to code in VHDL now. And I don't know whether you feel the same when you read these codes. Like basically, you describe what the hardware should do. That's all. In a single language, in a single sentence, you could describe the hardware. Okay. And by the way, this is a generic expression of how you define different signals essentially, but this is example. Typically, I feel like dealing with an example is easier than looking at these generic examples because they can be confusing. Okay, but they're there in case you need them ever. All right, let's take an example of a chain of multiplexer. For example, one multiplexer driving the other. All right, I mean, these are just random examples for you to get a grasp of how things work, and essentially, without any loss of generality. Okay, so let's consider this is your final output. So you have to define what this final output signal will be. So this F output will be A when your select signal is 1, don't you think? You see, we are describing that, exactly that. F is equals A, equals to A when A equals 1, as simple as that. But what if A is not equal 1? Just use else. Else, it will be, if E is not equal 1, for example, if it is 0, then there are two possibilities. It could either be B, or it could also be C. That depends on whom. Folks, tell me. So if, okay, let me just erase it again. If E is not 1, okay, I don't know if this is the best way to code it, honestly. I could have written, okay, if equals 1, do this, equals 0, do this, d equals 1. You see my point? And you'll see examples of that coming up as well. So there are different ways of coding it. Your friend will code in a different way. Your other friend will code in a completely different way. It's up to you. But I'm just trying to explain the code that is in front of you. Okay. And it is taken from textbook. It's not my code. So I don't want to comment on that. All right. So my point is, the way they have coded is, okay, if equals 1, just take A to the output. But if not, then what? Then there are two possibilities. You could either have C at the output, or you could have B at the output. But who decides that? This select signal, D. That's why your output will be B when D equals 1. Does that make sense, folks? If D equals 1, I'm so sorry, but this is bothering us a lot today. D equals 1, that means this B will go to the output. Okay? Does that make sense to all of you? Let's take a look at the 4 to 1 marks today, right now. And I've included different ways of coding the same thing. And you pick your poison. You can choose to do it this way, which is really nice and streamlined, or you could do it in some other ways. And there is certain, motivation behind each style, honestly. I don't want to get into that degree of detail. And honestly, you learn it by doing it over the years. And there are preferences that your team might have. If you work in an industry, your team might have a preference. So you try to fit the style that your previous teammates used. So, okay, I like one kind of coding, but everything else is coded in a certain way. So I try to match the style. That's the other motivation. Okay, so if you remember from our previous lectures, this is the expression for a 4 to 1 mux. Do you guys remember that? I vividly remember we did it in class. Okay, so imagine if this is 0, 0, you choose the first one. So how do I represent that? 0, 0 represents A prime, B prime, and I choose I0. So A prime, B prime, I0 is a term, which is in the first section, right? And you keep doing it for 4 combinations. Simple. So I'm going to define that. Let me zoom in here. So what does A prime mean? It means not A. B prime means not B. And I0 means I0. And you have to do end. So end and end. And just to make sure this is taken care of first, I use parenthesis here. Still with me? Don't give up. I know it's super boring. You don't have to tell me. And but trust me, as you work on it, as you code yourself, you can play with it. You could come up with different systems, and then it's fun, honestly. Okay, but it's not fun to learn about this random syntax because you don't have any control over it. Okay, let's just take another random term: A, B prime, I2. This is the third one. A is A, B prime is not B, and I2 is I2, and then you do end, and basically you put it in parentheses to make sure this is taken care of first. Okay, and then in between, wherever you had plus, you just define it as or. As simple as that. You describe it in plain, simple language. Okay, I'm sure, like when you look at this approach, it always makes sense to code using this direction, but there are pros and cons, obviously, as I said. There are more complicated circuits where having a list like this makes more sense than describing this in hardware, because we don't even try to get this. I'll explain in a second what I mean by that. Otherwise, it may not make sense. Let's go to the other example, and then I'll explain why that other example might make sense in certain scenario. Okay. Okay. Let's see. This is another approach. Set your function equals I0 when Tell me, when A and B are 0, 0, which one goes to the output? I0. And when it is 0, 1, it second one goes to the output. When it is 1, 0, third one goes to the output. When it is 1, 1, fourth one goes to the output. Basically, that's what you describe here. F equals I0 when A equals 0, B equals 0, and blah, blah, blah. See? As simple as that. But you have a long list to write. It's fine. Just copy paste and change the values. That's all. It's another way to do it. And there is yet another way to do it. This is another way to do it. Let me show you. So you deal. Oh, I forgot to mention one thing which you may or may not have noticed. How do you comment? You use this double dash and then add something after that. That's a comment. Remember that. Okay. So this is a comment. So you define a signal. You define a signal first. Say that signal here is select. Okay. So select is the signal, which is A and B. So A and B are basically two inputs that you have defined. And you choose based on the values of select. So A and B could either give you 0, 0. Think of the truth table of an AND gate with A and B input. 0, 0, 0, 1, 1, 0, 1, 1. These are the four options, right? Don't you think? So 0, 0, 0, 1, 1, 0, 1, 1. So basically, for each of these combinations, you choose which one is gonna, go to the output. This is essentially exactly the same as this one, but it is less descriptive. You don't have to like when A equals 0, B equals 0, like you have less things to write, essentially. You might wonder, hey, I don't mind writing this because it makes more sense to me. Honestly, I agree with it. But imagine when you're writing a very big code for an entire processor, right? So, saving small sections can add up. And more importantly, for simulators, in today's standard, we don't have to code this manually anymore. It's mentioned somewhere in the slides. You can read it. We use electronic design automation uh, you know, uh, electronic design automation frameworks that will do it for us, that will generate these codes for us. So, they don't care. They don't have to understand human language like this. Hey, do this when A equals 0 and B equals 0. They don't need that degree of description. So it's fine to just even further condense it down. All right. So let's move to the next example. I'm gonna now, like we are getting more serious and we are looking at a full-fledged module versus snippets. So far, we have looked at snippets, code snippets. Okay. Now we are going to look at full-fledged module that will learn in a simulator. The code snippets that you saw, none of this will run in an actual simulator because there are other components that's necessary. Okay. So we'll learn about that now. So I will talk about two aspects here. Number one, entity and architecture. So VHDL is called an entity-based language. So entity is basically a description of a black box, for example. So you define your component as a black box with some inputs, you give it a name. So the entity contains the input and output and a name, basically. And that entity could be a simple logic block, it could be a multiplexer, it could be an adder. You define what your entity is. So you define an entity, which is essentially a black box. Okay. And then you design the internal. So you don't know what's inside the entity, honestly. It's your circuit. That's the name, my circuit. But you define it as a block. I mean, block is a easier name than entity, right? I mean, it sounds like some kind of Marvel villain, like the entity or something. I don't know. Anyways, the point is that's what they use always, entity and architecture. So this is how you define an entity. You start with the term entity, and then you give it a name. It could be an adder, it could be multiplexer, it could be random circuit, whatever you want. You give it a name, and then you define its ports. So your ports here are A, B, and C, and you define whether it's an input port or an output port. Okay. And I haven't told you what this thing is. We'll talk about it. Standard logic. It basically defines the type of the data that is flowing through it. But we have a slide coming up which will talk about the standard logic. Oh my goodness. I'm trying to select this, but then okay. So you see my point here? And this is how you start. You start and then you end your circuit. You start the entity with a name, you end with the same name. Honestly, you don't have to memorize anything. Just keep it inside and just code on top of it. That's all. All right. So, and we'll see a full-fledged course soon. Code soon. But before that, we have to go through the architecture. After you had the entity, you have to define the internal structure of the entity. How are things connected internally? How many AND gates do you have? How many OR gates do you have? How are they connected? Who is driving home? So that's the architecture. Okay, that's basically the internal connections. So that's the standard of defining an architecture. So you give it any name you want. Again, you gave it any name, and we'll see an example of how different names can be meaningful. And remember, you have to use the entity inside an architecture because the architecture defines the structure of an entity. So this name comes from the previous stage where you define the entity. You know what? Let's move to this example first, where you have both of them side by side. It makes more sense. All right, let's see. So you have an entity description here. Notice this entity is given a name called two gates. It's not, I mean, don't blame me. This is from textbook. Okay, so they decided to give this circuit a name, and the name that they came up with is two gates. Okay, all right, two gates. So that's the entity. So when you define the architecture of this entity, you remember to call the same name, two gates, because you're defining that entity in the architecture. Does that make sense now, folks? Okay, so this architecture and entity will be side by side. They will talk to each other. Okay, now let's zoom into it. Zoom into this. And everything that you see here are described in the paragraph above. But I'm gonna describe it for you now. So this is your entity. Did I choose this? Yeah, this is your entity. And you see, you define the ports. How many ports do you have? You have A, B, D, which are input. So you have a set of ports colon input. And then you have an output, which is E. Notice the blue marked zone, you see the blue marked zone here? That's your black box. So you're looking outside the black box. That's why you don't see C inside. That's inside the black box, right? So you see A, B, D, and you see E. That's why you define them. A, B, D input, E output. Does that make sense, folks? All right. By the way, what is that? This represents the type of data they're dealing with. It's a bit. The reason I say that is you're dealing with one bit at a time, say 1, 0 or something like that. You could also deal with a stream of bits. It could be 1, 1, 0, 1. So that is also possible. In Verilog coding, instead of dealing with each bit at a time, you could deal with a stream of bit at a time. Okay, that's why it could be bit stream. There could be other data types as well. But for the most part, you don't have to worry about it. It's typically bit for our purposes. That's why it's a type of bit. We are dealing with bitwise operation here. Okay, so now you finish your entity description. This is your entity description. And now you are defining the architecture. Okay, so you give it a name. And the name that they gave is gates. That's it. That's the name that they came up with. You could give it any name. But remember, do I have any control over this name now? Once you have defined the entity, it has to be the exact same name because the architecture is for the entity. Remember that. Okay. All right. And now notice, this is interesting. This is new. You define a signal called C because this is an internal signal. Whatever you define inside the architecture, that remains internal. That is not an external input or output port. Remember that. So that's where you define C. And this is also a bit type. This is a bit type port. Like you basically deal with bits again. Okay, then you define C as A and B. As simple as that. C is nothing but A and B. And E is nothing but C plus D, which is C or D. We have been seeing this snippet so far, haven't we? We didn't see the way this thing is structured. You define an entity, you define an architecture for that entity, and inside the architecture, you have the snippets that we learned. How do you define AND or how do you define multiplexer? Everything goes inside the architecture. Entity only tells you how the black box looks like. What are the inputs? What are the outputs? What is the type of data that you're dealing with? Are you dealing with one bit at a time or are you dealing with streams of bit at a time? Does that make sense, folks? Okay, so I think this is we just have 1 minute anyways. We can stop here and I can move over to examples like full adder, for example, in the next class. Okay. So thank you for listening. And I'm sorry for being a little bit